So in this video we are going to finish off the main part of the A* tutorial. So we will have a path that we can actually follow when we're done with this part. But there are quite a few steps we'll have to do in this part of the tutorial. So to make it easier, I will refer to the video I created. And the step we are at right now is step 7, where it says we need to continue the search by selecting the node with the lowest F-score from the open list. And what we did last time was make us able to click 2 places and then have all the information for every single value that we need to do the search. So let's try to open up our A* script, because here we need to add some more information. And when the script is open, we will go to A*, and then we need to go to our getPath function. And in here there's a few things we need to do. First of all, we needed to add step 7, which says continue the search by selecting the node with the lowest F-score. So to find the node with the lowest F-score, we can actually just sort the list and then simply select the one that is first on the list. And there's a very simple way of doing this. We should do it after we have taken our current node and removed it from the open list and taken it to the closed list. And then we can say, because now our current node is not on the open list anymore, so we're not going to use that to find the node with the lowest score. So we can say if our open list count is larger than 0. So if we have a count that is larger than 0, well, then we need to continue this operation for finding the node with the lowest F-score, right? And then we can say our current node is equal to open list dot order by. And as you can see, we don't have anything called order by here. That's because it's in a namespace called link. And link is just some operations you can do on sets like lists and stuff, right? So you can right click on order by, quick, and using system.link. If you can't do this, remember you can always go to the top here and write using system.link. When you have done that, you can actually write open list.order by, and then we can make a Lambda expression. So every time we find something, we could also do this in for each loop, but I think it's more neat just to do it in one line. But we could do a for each loop that runs through the whole list, or not for each loop, sorry. We could sort the list by ourselves, and then we could take the one with the lowest F-score, which is on top of it. But we are going to use this Lambda expression instead. So we are going to call every single node on this list n, and we're going to look at n.f, and we are going to find that one which is first. So basically what this does, it takes the whole list, orders it by the f value. So every time we find a node on the list, we called it n, so we can examine it, and then we take the f value, and when we're done with that, we take the first object on the list, which should be the one with the lowest F-score. So basically what this does, sorts the list by F value and selects the first on the list. So we sort it by F value, and the one with the lowest F value will of course be first on the list, so we take the first one out of the list. So this is basically step 7. So this is step 7. What else do we need to do? Let's try to move along here. And 8. Move the node from the open list to the closed list. Well, the way that we wrote this, we actually already did that up here. So basically we can also say that this is step 5 and 8. This is 5 and 8, because we're already doing here. There's no reason to write the same code again. And that's just because of the way that I set it up when I wrote this. That's step 8. Let's see what else. Step 9. Examine all neighbors. Ignore unwalkable nodes on the closed list. Nodes and unwalkable nodes and nodes on the closed list. Okay. So here we need to write some more code, and we can actually do it up here. We already have an if statement here, but we will change that around a little. Basically, we should make an if statement here that says if our closed list dot contains our neighbor. So we need to get a reference to our neighbor, and we have that up here. So if it contains our neighbor, or if it doesn't contain our neighbor, I mean, well, then we need to do something, because it says here that we need to examine all neighbors and ignore unwalkable nodes and nodes on the closed list, right? And up here we are actually examining all our neighbors, and this will be put into another loop, so we run this again. So we examine all our neighbors already. So this part of the step is already done. Ignore unwalkable nodes. Well, we are already ignoring the unwalkable nodes in this if statement here, right here, because we say that it should be walkable. So we can't get to this code down here without checking if they are walkable. So that is also done, this part of this. But nodes that are on the closed list should be ignored. We haven't done that yet, and that's what we're doing with this if statement here. We are ignoring nodes that is on the closed list. So the node we're checking should be on the closed list. So this part is actually step 9.1. Okay, what else? Then we need to go to the next step. Let's see what we want here. Still the same. Here. That's 3.2. We need 0.2 somewhere. Let's just play it here and let it go. I can't hit 2. There we go. Undiscovered neighbors are added to the open list. Okay, so neighbors that are not on the open list already needs to be added to the open list. Let's see. So we can basically go in here and say open list dot add neighbor. So this is step 9.2. But wait a minute, nothing says that this neighbor is undiscovered, and that's true. We're never checking if it's undiscovered at the moment, but we will actually do that in a second, because this if statement here will turn into an else if statement. We can actually already do like this: if open list dot contains neighbor, like so. So if our open list contains the neighbor, then we do something in here, and we'll do that soon. But else if the neighbor is not on the open list, well, then we check if it's not on the closed list, and if this one is false and this one is true, well, then when we get in here, then it must be a new neighbor, right? Because it wasn't on the open list, and it's not on the closed list. So if we get to this point, it should be a new neighbor, because it will only execute this code here if this one is false, and if this one is false, it's a new neighbor, and if this one is false as well, it's true because it's negative, then this down here should be a new neighbor. So this is actually step 9.2. Maybe it's a little confusing, but that's just the way that I like to set it up. You could do this in longer if statements, but I like to reuse the code. So basically we just take the A star and move it a little around so it fits our needs better. Yeah. Okay, so that's this step. Undiscovered neighbors are added to the open list, and that's exactly what we did here. Right here. Okay, what else do we need to do? Let's see. Then should be step 9.3. Set the current node as parent to the new nodes on the open list. Calculate f, g, h values on the new nodes. Okay, so basically we just need to say neighbor dot calculate values. The current node should be parent, and the goal is nodes goal, and this is the g cost. There we go. So now we have all our calculated values, because this calculated values will set the current node as parent, and this will be used to calculate the g and f and h values here, right? Because we already created this function for us. So this is actually step 9.3. Okay, so let's take a look at what else we need to do. So now we have set the current node as parent. and we have added those to new those on the new list, and we calculate f, g, and h values. Okay, so the next step would be, if I can read that down there, just going to maximize, you can't really read it. Let's see. Okay, check all new neighbors on the open list. Is the current node a better parent? And then if the G score is lower, we can use the current node as a parent. Okay, so we need to check the G score to check if this new node is a better parent than the original parent. So let's do that. We can actually do that right here, where we do it up here actually, because I would like to do this before, as inside here, before we actually do this down here, because it makes sense to check the G score before we actually start doing this, because we have already checked here that it already is on the open list, and this one states that it shouldn't already be new neighbors. I think that's a little mistake, because it needs to be neighbors that are already on the open list. Those are the ones that we need to recalculate to check if they are needs to have a new parent, right? So all neighbors on the open list will need to be recalculated to see if the new node here is a better parent than this one up here. And here we know that the node is already on the open list, which means that it has a parent already, because if it's added to the open list, we have a parent. And then we need to check if this current node is a better parent than the ones they have already. So here we can actually just say if the current node .g plus g cost, whatever it costs to move over there, so it's original g plus the all cost, is less than the neighbor .g. So if that's the case, well, then we need to say neighbor .calculate values, current node, nodes goal, and then the g cost. Because if this is true, then our current node is a better parent. So we can actually say set the parent here with calculate values and recalculate the g, f, and h score here. So this basically remaps the parent on the node. So this is actually step 9.4 we have here. Okay, so let's try to continue. Still 9.4. Let's see, got some other. This is 10. Okay, continue the search from step 7 until the open list is empty, no path available. Until the goal is added to the closed list, we found a path, or the path can't be found, and then the path can be found via backtracking. It's a little hard for me to read here because there are some things in the way. Anyway, so we need to continue the search from step 7 until the open list is empty, or we don't have a path. So let's do that. First of all, we actually need to make a while loop around here. So basically we can make the while loop here, and it needs to continue until the open list is empty. So we can say while open list dot count is larger than 0, because then we have something in the open list. And then we basically need to take everything we have and put it into this while loop here. So we can go all the way down here to before we do the debugging, and move all the way up here and cut it and then paste it in here. So what we have now is a while loop right here that goes all the way down here. So everything we wrote so far is inside this while loop. So this is basically step 10, some part of step 10, right? So that was this part. So we need to check if the goal is found and so on, and we need to check if there's no path available also. So how do we do this smartest? Well, let's go to the bottom here, and after step 7 we can actually say if our current node is equal to the goal. So if we find if the current node is equal to the nodes that is actually the goal, well, then we should be done. Then we are actually done with this. So we can actually just break here, because then we're done searching, right? Then break the for loop because we found it. So we just basically until the goal is added to the closed list, right? And if the current node is the goal, well, then it's basically added to the closed list. So we need to create a final path somehow so we can show it to the player and we can return it to the monster so they can actually move around on the map. So we need to go to the top here. Where do we have it? We have closed list. We can just make a new stack. And the reason that I create a stack is because we need to backtrack through the final path. And the easiest way to do that is to have a stack so we can pop it. Because a stack has everything placed from top to bottom. And when you say push, you add something to the stack. And when you say pop, you take the first item off the stack, right? So let's say we have a node 1, 2, and 3 here. If I create a stack, just do it like this. If I create a stack with nodes and call it final path equals new stack, then I can add something to the stack by saying final path dot push. That's what you use to add something to the stack. So if I want to add something, I can say path dot push, and then I add something. Let's say one node here. Now this is not right, but let's just for showing. So this adds node 1, right? And if I do the same again, down here I add node 2, and this adds node 2. So if I need to get something from this, let's say that this is our final path we have added, then I can say final path dot pop, which will remove node 2, because that's the last one that was in it. So it's like a stack of papers, right? You put down the papers on the table in a stack, and when you say pop, you take the top one and remove it from that stack. Which means that we will get the last one off. So let's say we add the final path. Yeah, I don't know if I can run this now. Yes, I can. Let's say we have final path here. All these nodes are added, and this is our final path. Then I can start popping. So I pop this one, pop this one, pop this one, because this one was added last, right? So I can actually pop them all the way to backtrack to my goal here, right? So basically I can take the stack and reverse it, and then I can go, I'm standing here, then I pop the first one and move here, pop the next one and move here, pop the next one, and so on. So that's how I can backtrack the whole way, or get the whole path. That's just like little theory about how a stack works. Okay, so now we have our final path here, and we need to do something with it. So down here we need to say final path dot push our current node, right? So we have our current node in the final path now. Then we need to say our current node is equal to the current node dot parent. So what happens here? Well, let's say that we have just found our goal here, and this is our current node. To add the and this one is added to the final path. To find the parent, we say current node dot parent. Then we jump over here and add that to the path. Then we say this node dot parent. We jump over here. This one's parent. This one's parent. This one's parent. So now all the path here is actually added to the final path stack. So we have the whole path we need to move through to find the goal. So this is exactly what we're doing here. And basically we need a while loop here, so we can say while our current node dot grid position isn't start. Okay, and the reason that we're doing that is because we move from here parent, 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 and at some point the current node is equal to our start position here, and then we don't need to backtrack because this one doesn't have a parent, and if we try to get the parent, we'll get a null reference, right? So at some point when we jumped all the way down here by current node dot parent, current node dot parent, and so on, we will get to this one, and then we stop, because then we have found our whole path here. And we're basically almost done now. We just need to do two things. We need to show the final path to the player so that we can see it works, and we also need to delete something, because I just remembered that I rewrote this if open list contains neighbor up here, and this is actually the same if statement as we have here almost, because this basically has changed the little code, so we don't need this down here. So actually underneath the if and else if statement, if you have some code here, open list contains neighbor, open list.add, and neighbor.calculate values, you can actually delete it because this is already done right here and right here and right here, right? So we don't need to do the same thing. And then I think we'll get an infinite loop if we have it down here. So this is actually how, maybe it's hard to see, this is how these two for loops should look like right now. And then underneath we have all the open list, remove and add and so on. Okay, so we can try to run this and see what happens. Let's try to do this. Click and click, and then we get an infinite loop because I think I forgot to save. Let me just close down Unity and reopen it. And I just reopened Unity. Let's try one more time to see. Click and click, space, yeah, there we go. So now it actually shows our path, not correctly yet, but we will do so that we can see the actual path here. So but you can try to click different places and you'll see that it actually finds kind of a path here. You can find it through the closed list, but that's not totally correct because the closed list isn't the final path. So we'll have to show the final path as well. But now you should be able to get something that looks like this. I am going to end this video here. In the next video we will take a look at some corner cutting, and we will also be showing the final path to the player so that we can actually see that the A-star algorithm works. So thank you very much for watching, and don't forget to subscribe to the channel, like my Facebook page, and follow me on Twitter. Also remember that InScope Studios is a community found page, so all your support is very important to me. You can support me in different ways. You can support me on Patreon. If you do so, then you can get every single project that I've ever created. And you can also support me by buying one of my projects as a standalone product in the bottom of the screen. So thank you very much for watching.